Okay, everyone, welcome to week 8 and lab 7. Today we're going to be going over soil texture and water budget. It is going to be a little bit of a longer of a lab with a few random terms, so I'm going to go over this PowerPoint in one video, and then I'm going to upload a second video where I work directly on the lab and give you an example of a few of the and walk you through a few of the questions, just because I do think they are a little tricky and they may lead to a lot of questions. Remember, before I go on, that exam 2 is next week. So yeah, just remember that exam 2 is next week, and that is going to be covering from labs 5, 6, and 7. So next week, yeah, just remember it's next week. Okay, so for the experiment today, we would usually be doing this in class, of course, but we're not. We are working to classify a soil sample, and you'll understand more about how we classify that in geography a little further along this presentation. But this experiment is essentially we're adding some stuff to a sample of soil, and the stuff we add and how it reacts with the soil and dilutes with it over a 2-hour period is going to give us the percentage of different types of soils in this one soil. So the soil sample we're looking at, here's a picture of it. You could see what we're going to conduct our experiment on. This is 50 grams of soil. So I already wrote that in your lab. It's 50 grams of soil, but just for your reference, this is what the picture would look like. And so our other materials that would be using are a watch, so maybe a stop clock on our phone, or if somebody has an Apple Watch, a dispersing cup, so that's the cup right over here on the left side, 100 milliliters graduated cylinder, and then the dispersing cup, so you would put the cup into a little malt mixer. And we also would have to use a hydrometer, a thermometer, sodium silicate, and a stirring rod. So we would have our hydrometer over here. It's a little bulb. Oh, I'm sorry. It looks like a thermometer, but it has the bulb on top. And then we have the thermometer that we've used in other experiments before. And both of these pictures are sodium silicate, not great to get in your eyes, and then our stirring rod. And how this experiment would work, we would place in the dispersing cup 300 milliliters of water and 5 milliliters of sodium silicate. We'd pour into that cup right there. Let me get my annotation out. Okay, there we go. So we would pour the sand, the water, and the sodium silicate into this cup. We would disperse it. We would transfer and fill it into this graduated cylinder and measure it to the 1,000 milliliter mark, somewhere around there. And then we would want to use this rod, mix it all up for about a minute or two, not very long. And then we would transfer it into this cup and we would let it sit for a little bit. And our first measurement of the thermometer and the hydrometer would be after 40 seconds. So we would write those numbers down. And then we would wait 2 hours and take those exact same measurements from the hydrometer. And it doesn't say here, but the temperature. And then we would be done with the experiment, get our data, and move forward. Let me get rid of all of those annotations for you guys. Clear all. All right, cool. Let's go on to the next one. So then we would do experiment data. And then after 40 seconds, I'm going to give you guys these numbers because obviously we're not in class. So experiment data after 40 seconds, the hydrometer measurement was at 21 grams per colloids per liter, and the temperature was at 20 degrees Celsius. At the 2-hour mark, hydrometer was at 8 grams per colloids per liter, and temperature was at 21 degrees Celsius. Down here, it says read the instructions at the top of the page and learn how to calculate the adjusted reading. We're going to do the 40-second one together. And then I'm gonna leave the 2-hour one for you guys to do. But after this video, I'm gonna go on to lab 7 and work through one of those adjusted readings with you guys. All right, so and then after we get those adjusted readings, we're just gonna have to classify the soil based off the readings we got, which we'll learn how to classify soil in the second part, the latter part of this presentation. But yeah, so make sure to tune into that second video. It'll make that getting those adjusted readings a lot easier. But okay, let's jump into it. What is soil? Soil is a mixture of fine rock particles, about 45% mineral, and organic materials, and it's formed by complex physical and chemical actions. And the properties at any given location are important in determining plant life. So vegetation, hydrology, how the water flows, and animals like humans. So based off the soil of an area, it's really going to dictate what's capable of living there. So let's look at now what is a soil. So it's about 25% air, 25% water, 45% mineral particles, and then organic matter is our remaining 5%. And here is an example of the types of organic matter over on the left side that could be found in soil. So let's look at soil texture now. So soil texture, it's composed of 3 different size particles. First being sand, second being silt, third being clay. Sand is the largest of these particles at about 0.05 millimeters to 2 millimeters. Silt, it's the medium, it's the smaller, but it's the medium particles. And then clay is the most fine particles. So if we're gonna go from greatest to least, the largest particles is sand, the medium sized particles is silt, and the smallest ones, so the most fine ones, are clay. All right, let's check out this soil classification triangle here. So different classes of soil have different characteristics. An example was, if you look into the middle bottom of this pyramid, you'll see that loam is a classification. It's really good for agriculture. And then by determining the percent of each soil type in the sample, we can classify the soil and figure out what might be best to use the soil for, what might be best to do, and maybe crops to grow in a certain region. So let's look at an example. What type of soil would be 60% silt, 10% sand, and 30% clay? All right, let's work through that together. Let me get my little annotations out. I'm gonna show up. There it is. Okay, cool. So let's first look at the 60% silt. So come over here. Our silt should be right there. And we're gonna go to 60. So we choose 60 and we see that it can go this way or this way, right? Our silt can, based off this 60, it has 2 angles because we're using a triangle. And then let's go to the next one. So sand, we have our percent sand. Let me change my color, so green. So then we're gonna look at the sand. It's 10%, so let's go over here, find this 10% sand. Go ahead and trace it up. Okay, now we have 2 angles that it possibly hits from the silt. And then lastly, let's look at a different, let's use a purple, I like purple. Clay, 30% clay. Our clay is over here, right? So 30%, we come on down here and we're gonna cut this first angle. I think we got a winner right there. And then our second one comes down here. So right here is where they all intersect, and that is our classification. And it is a silty clay loam is what we would classify this soil as. And if you're doing this, a ruler can be fun, easy, make things, lining things up a lot easier, or you could just sketch like I just did, whatever is easier for you guys. But yes, that's how you would find that's how you would classify that soil, that percentages of soil. Okay, let's see. Yep, there we go. As I showed you before, silty clay loam. Soil classification triangle part 2. Let's do some examples together. Let's break out the annotation again. Let's start with red. So actually I want to start with pink. Okay, so 40% sand. Let's look at this first example. 40% sand. Come down here. Got our sand in pink. 40%. There we go. Got the 2 angles it could be going through. And then let's go to a different color, purple, 20% clay. So let's go over to the clay, 20% or right down here. So we got this line. Oop, got 2 winners from that 20%. And then lastly, we'll use a blue. We have 40% silt. It's right here, right? So we're gonna come down here. Looks like we got a winner. And that's gonna be our classification. So this is a loam, right? That first example is a loam. It lands right in the loam. That's where those 3 percentages intersect. Okay, let's do the second one. We'll start with blue this time, 15% sand. Okay, we have our sand down here, 15%. So let's find maybe like right in the middle. All right, between 10 and 20. We have 65% clay. 65, about right there. Come on down here. Oh yeah, I forgot to do that second line for the sand. So remember, we're gonna have 2 coming out each way, about as a triangle shape. And we could use pink for the last one, 20% silt. Put our 20 here, right through the middle, right? Clay is our winner. This is a clay. This last one is a clay, which if it's 65% clay, we probably could have made an educated guess that it was classified as clay, but just to be sure, we go ahead and classify it using the triangle. All right, let's go on to the next one. Okay, soil permeability. So permeability refers to how easily a substance, we're going to be talking about water in this lab, can move through the soil. So high permeability leads to lots of water movement, right? So high permeability would look like this image on the left. So when you think high permeability, it would only make sense that if water is able to move through this soil quickly, the particles would be bigger. So usually, let me go ahead and get my annotations out here. Okay. So usually high permeability is associated with lots of movement, free movement from the water, and sand particles, because sand is the biggest particles. Low permeability, on the other hand, is usually more associated with not as much movement. Let me make sure I spell that right. And smaller particles. So clay, right? Clay was the smallest of our particles. So the larger the particle size, as I mentioned, the faster the water can move through it. So sand, water has the most movement, high permeability. Silt, it's a middle ground, and clay, it has the least amount of movement going through it. Let me make sure to clear out those annotations for you guys real quick. Clear all drawings, perfect. All right, so now we're gonna look at soil water budget. It accounts for all water that leaves, enters, or is stored in the watershed. A watershed is any area of land in which all the water flows to the same discharge point. It's usually an ocean or a lake. For example, the San Diego River, that's a typo. San Diego River watershed is about 433 square miles. Okay, so soil water storage in this watershed. It's essentially we're measuring how much water can be stored in this soil in this given watershed. If soil water storage is full, the soil is saturated. So it's like if you were mixing sugar into a cup of water, at some point the sugar is going to stop dissolving, right? Because the water is fully saturated. Same thing could happen with soil and watersheds. So at that point, if the soil in this watershed is saturated, any more water entering the system then flows off and is a runoff out of the watershed. Let's look at the inputs versus output. So the major input is precipitation, so rain essentially. It's the amount of water that enters the system, so enters this watershed. So this is the input to the soil budget. So the P is the input, the precipitation is the input to the soil budget. Let's look at the outputs now. First type of output is evapotranspiration. So evapotranspiration is evaporation, which I feel like we're all familiar with, and transpiration. Transpiration is just plants breathing. So the evapotranspiration is the source of output in this water system. There's two categorizations of this evapotranspiration. The first is actual evapotranspiration, and that's, let me go back, is denoted by the letters AE. And that's how much water is actually evaporated based on how much water is actually available. So how much water is disappearing or leaving the system, and the actual measurement is AE. And then there's potential evapotranspiration. That's denoted by PET. And that's how much water could potentially be evaporated if there was abundance of water in the system. This is heavily dependent on temperature and how much access the system has to water. Okay, now let's check out the surplus versus deficit. So we're going to look at the surplus first. Surplus, there's two categorizations of surplus. One is recharge, and that's when soil moisture storage is being refilled to full. So let's imagine this watershed. It's been using this water. Some plants have been growing on the banks of the river. Water's been washing out, and then it starts raining. So to be an example of a recharge, it's when P, so precipitation, is greater than the actual evapotranspiration. So you're getting more water into the system. It's equal to a recharge. It's recharging the system, this watershed. Then we have a surplus, and this is when you have more water entering the system than is leaving. And the soil moisture storage is fully saturated. So this is when the soil and the system is so saturated with water, there's going to be a runoff. There's going to be an abundance. It's as much as the system can use, it will use, and the rest will be released. So this is when the potential evapotranspiration is equal to the actual evapotranspiration, right? Because the potential amount, since it has an unlimited or so much extra, is going to be equal to how much it's actually using. Okay, now we have now we have the deficit side of the surplus versus deficit. So deficit, much like the surplus, has two, and the first being utilization. That's when more water is leaving the system than entering. It's when the actual evapotranspiration is greater than precipitation. So it's being utilized, utilization. Then we have deficit. That's when water is leaving the system, but not at a full potential rate. Eventually, though, the soil water storage will be exhausted. That's when the potential evapotranspiration is greater than the actual transpiration. So a lot more is leaving than is actually allocated to be leaving. So although it might be getting filled up in small points throughout over a period of time, eventually the soil water storage is going to be exhausted because it's using more than it actually has available to it. That's a deficit. So this all plays into the soil texture and water budget. So as we went over early, tightly packed soils like clay, it allows less water to enter the system because it's less permeable. Precipitation often becomes runoff, and water drains slowly out of the watershed. Loose soil, sand, water is easily permeates and enters the system. Less water because more is being absorbed. And water will drain out quickly. It'll get through the sand really quickly because the particles are so big. And plants and vegetation do the best with a balance of both. So the loams, if you remember that triangle we used for the classification, right in that loam category is where vegetation thrives. The soils with a good mix of textures are the best for farming because they want some water to enter the system, and they want it to sit for a little bit, but they don't want it to take forever to get through, or they don't want it to just rush right through. So it's a happy medium. So the areas of moderation are best for crops and agriculture. All right, so that's the end of our lecture. Remember, exam 2 is next week, and that will cover labs 5, 6, and 7. And then please do check out the other video I would recommend before you do the lab. But if not, and you feel like you got it, more power to you. Go ahead and get it done. Good luck this week, guys.